Good morning to all of you. First of all, I thank Shekar sir and his colleagues for inviting me for this workshop. So the topic that was discussed and finalized was neural network for video analytics. Actually, the plan of the presentation is as follows. So today, first two sessions, I will be giving a basic introduction to the neural networks and how this neural network can be used for video analytics and limitations of the neural networks and how this motivates for deep neural networks. Actually, what we have planned is tomorrow we have Dr. Dinesh we are from the same company. Is my senior, so he will be delivering lecture on deep neural networks. So what we both planned is like first we will give an introduction to neural networks, and then we will today we will finalize how neural network can be used for video analytics, simple use cases and all those things, and with the limitations. So I will be winding up today's session with a motivation like what is the limitation of the neural network, and tomorrow Dr. Dinesh will explain how this limitations of neural networks were motivated to develop the deep neural networks. So first, he will explain about the deep neural networks for different use cases of video analytics. So overall, my presentation is into, I have split it into two presentations. In the first session, I will be delivering on principles of neural networks. And next, I will take a case study of video analytics on video archival and retrieval the system and object detection in videos. So along with the demo for both the sessions, the code I have shared already, I got several requests. Probably it may take some time because I am in the session. I may not be able to provide you the access to the code. So after this session, I will provide access to everyone. So don't worry about that. Okay. So now let us start with the discussion. So first we have to understand what are neural networks, or why sessions are required when we are having a workshop on video analytics. So nowadays, most of you may be knowing that in the field of artificial intelligence, the important domain or area of artificial intelligence is ruled by deep learning. So deep learning is a subset of a neural network, means, or it's a advanced versions of the neural networks we can see. We can say that's why I am going to give you a brief introduction about the neural networks. So, what are neural networks? As we all know that we human beings are more intelligent than any other animals on the earth. Some in some perspective. Okay. So, what makes us intelligent is our thinking capability or a problem solving capability. So, this thinking or problem solving capability has been developed towards ages. Means our brain has been developed. Means entire human system has that brain and nervous system, which is the main responsible for making us more intelligent than any other animals in on the earth. So similar to that, yeah, in the field of artificial intelligence or machine learning, so try to mimic the human brain. So this neural network is the actual model of a human brain and nervous system. As we all know that human brain consists of numerous neurons or some types of cells which are well connected throughout the body through a nervous system. The neural networks are similar to human brain. They have a certain set of components similar to neurons, and they are well connected. And they will. We are trying to mimic the human brain. Till now, we have not succeeded to the level what a human can do. But somewhere we are still we are in the infant stage. So let us try to understand how this neural network and human brain systems are common, have some commonalities or how it will work. So we can do a task in parallel. Means I can think, I can write together. Like a person can do multiple things in parallel. Same way, these neural networks are also capable of doing the task in parallel. Like unlike machine learning algorithms, they are serial. Means if you see the architecture or the way of they learn, it is a serial process. Whereas this neural network, a special kind of machine learning algorithm, has a capability to learn the things in parallel. Or when I say learn the things in parallel, means it can be implemented in a parallel way so that it will be very fast. And comparing to other machine learning algorithms, the neural network is capable of learning the data in different situations. If we take some machine learning algorithms, may not be work when we have missing informations. But a neural network is capable of learning the data even when we have missing informations, and also it is capable of generalizing the data. So means the neural network can learn on the seen data and capable to do inference on the unseen data, even though unseen data are not part of the population or distribution of the training data. It to some extent, or it's not some extent, it's to a very good extent, a neural network can generalize the data and do the task of either classification or clustering or any type of learning mechanism. And coming to the implementation of the neural network, it implemented using very simple principles, mathematical principles, like simple summation would be worked when compared to other which are having more complicated understanding, means mathematical these things. So it's a summation of just a sum of product values of algebraic functions. Using this itself, we can develop the neural network. And also this neural network is capable of understanding different kinds of data. It's not only one type of data, like it can understand image or non-image data, like textual, video, audio, or tabular type of data, structured data. And also it can understand the complex behavior of the data set. Means it can work in different situations, starting from simple to complex structure of the data. So when I say complex structure, like it is capable of capable of learning both linearly and non-linearly separable data. In machine learning, whenever we say data, mainly while doing the data analysis, first thing we will see whether the data is linearly separable or non-linearly separable. Because for any machine learning algorithm, the main part or crux of the algorithm is identifying the decision boundary in case of supervised learning. So that time we need to identify whether the data is linearly separable. When I say linearly separable, means I separate the data using a simple straight lines. Means the boundaries can be drawn using a simple straight line, combination of different straight lines. Or if the data is too complex, whether in that case straight lines cannot be used to identify the boundaries, then we have to go for non-linear representation, like curves or arcs, something. So neural network is capable of doing both linear and non-linear separable data, understanding that one. And coming to the application, as I said, it is a very good problem solver for many applications. Irrespective of the data type, this neural network can solve the problems if we provide the data in a proper format with a proper architecture and all those things. So in today's lecture, we are going to understand all these things one by one in a simple manner. I know that the entire session will be basic. Like I came to know before the session, I understood that there are more than 100 participants with different categories, like starting from students, master's degree students, research scholars, or assistant professors, and so on. Probably, I assume that the distribution is normal, and majority of the people are new to the neural networks. So it will be not an advanced presentation. It will be a basic presentation, whatever I am going to discuss today. So just to understand how this biological neural networks and or artificial neural networks. So artificial neural networks means the neural network which is designed in the computers. So in 1995, Van Tebe did an experiment. So a pigeon was taken and put it in a box, and he started showing paintings of two artists, Chagall and Van Gogh. So he wanted to identify, means the pigeon was supposed to identify the painting, whether it belongs to Chagall or Van Gogh. So what he started doing, he started rewarding the pigeon by giving some peanuts or something whenever it was able to identify, means whenever he showed the painting of a particular artist, example Van Gogh. So then, if was from Chagall, he was not rewarding the pigeon. Means the pigeon try to understand, okay, so if the painting is from particular structure, my owner will give me some rewards. So it was trying to memorize that one. It's just like a training. So he tried to do that one, and after that it was about a testing. So he tried to show the paintings of different, means both the artist, and if it was able to identify, means if it was able to pick that one, so it was rewarded. So on the training data, this pigeon was about 95% accurate. It was able to identify the Van Gogh and this one Chagall's painting. So on the unseen paintings, so it was about 85%. So what this experiment says, that means our brain is able to identify the patterns. Means we are able to extract the basic components and recognize the patterns, the styles, and generalize it. So if I want to say about the artificial neural network, it is the same. Like we will be having a training and the inference or testing. So in case of training, what we will do, we will try to provide a huge amount of data to the system, means to the network. So it will try to learn. So after certain amount of training is done, we will try to show the unseen data, and we will see that how it is able to recognize it if it is a classification problem. Same way it can be extended for any type of learning algorithms. So keeping in this mind, artificial neural networks designed, it has the same structure. Like in case of biological neurons, biological structure, we have neurons and synapses. Neurons are nothing but a special type of cells which are connected together by synapses. So in case of artificial neural networks, so we call those neurons as nodes and synapses as the weights. So entire neural network is made up of only these two components, neurons and synapses. So we will try to understand how this neuron works, or how these weights are identified. We can assume that it's just like a graph as shown in the figure, and the circles are the nodes and the lines are the connected, the edges along with the weight, these things. So we will try to see this one. This is the simple structure of a neuron versus a node. So a neuron, it consists of a nucleus and a cell body, which is connected to other nucleus or other neurons through connections. Okay, so this nucleus or neurons will contain some type of informations. So these are the responsible in human brain to store the information. When I say it stores the information will be in a form of electric impulses. So how much cell is in an active state. So whenever we see or something, the cells becomes active. Based on the active, an entire structure will be created. Same way, in case of a node like artificial neural network, we
Has
will be
joined the
having
meeting.
a node. We are having a node. A node is connected with several inputs, okay, and it produces a output. It's not like that it should produce only one output. So one node can be connected to multiple nodes. So this is a simple structure node. So we can understand. So a node will be having a set of inputs and it produce set of outputs, okay, whereas in the diagram I have shown only one output. Okay, in general it can have multiple outputs also, and this node will have some functionality, means it do some functions, and it try to generate a output. It's just like our function which takes certain set of parameters and do some operations and produces the output. So this node will be responsible to make whether the circuit, like if I take this entire neural network as a circuit, whether the next connected node should be active or not. So it will try to send a electric signal, or it will try to send some values. So that value will be the weights of the edges. So how it works? So the structure of a node, as I said, it will take a input and it will be having a function. So normally it is called as a squash function, okay, and it generates a output. So this squash function is just a function which takes a input like 4.7 and do some operations. So it's a simple mathematical function and it produces a output. So that's all we have to understand. So overall the node consists of a function. There is a function f of x. Instead of a squash function, we can write it as f of x. X is the input, f is the function, and entire neural network depends on how or which squash function we are going to use in what a situation. And also the neural network depends how we are going to create a structure. So now let us try to understand. So normally networks are called as feed forward networks because it will take the data from the input layer. So in the neural network, we will be having something called as an input layer, which is responsible to accept the input from the external system. So it accepts the input and it will pass on to the next layer called as an hidden layer, okay, and then these hidden layers will do some sort of operations and generate some output, and those output will be passed on to the last layer called as output layer, which is responsible to give the expected output depending upon the type of the data or a type of the problem we are using. If it is a like a problem, it will try to give the class labels of the input data, or if it is a regression problem, it will try to give the predicted values and so on. So overall, the neural networks, it consists of three layers: input, hidden, and output. And always it is a feed forward, means the data moves from input layer to the output layer
Has
through
left the
hidden
meeting.
layer. So here, the information is unidirectional, as I said, like it's from input layer to the output layer. And very important thing about this neural network is information is distributed. So let us say we got the input. So let us take an example of iris data set or some other data set, some data set which has three features. So the input layer will be having the number of nodes. The number of nodes in the input layer will be always equal to the number of inputs that we are giving to the neural network. So that will take and it will try to send the data to next layer nodes. So it has been distributed to multiple nodes. So each node, if you see the first node in the hidden layer, it has taken the input from all the three input layers and it will try to do some type of operations. Same way, all the layers, all the nodes in the hidden layers, it accepts the data from the previous layer do some operations. Now you can see that the data has been distributed to multiple nodes. So these nodes do some type of mathematical operations, and then it will pass on that data to the next node. When I say it pass on the data to the next node, it indicates whether the node in the next layer should be activated or not, or to what extent the node should be activated. In this process, what it will do, it will try to identify, the neural networks will try to identify the weights of each edges. So the edges are connected between the nodes. So the entire neural network responsibility is to identify the weights. So the input is given by the user. So the neural network will try to identify the weights based on the type of the data and type of the problem, and it will try to see like how much the node should be activated. So I said that in the beginning, this neural network is parallel. Like you can see that information processing is in parallel. It's not like one node by one. So it tried to learn parallelly. And also, the very important thing in this representation is the internal representation of the data. Initially, we had a data, let us say x1, x2, x3 as an input data, right? After that, the data has been transformed to hidden layer. Means in the hidden layer, the data has been transformed to some other format. So that we will try to understand. I have a demo and explanation about this internal representation. I will show you like how the internal representation will be there. So this internal representation, it can be a higher dimension than the input data or on the lower dimension, right? It depending upon the number of nodes, and that data will be passed on to the next layer. So output layer always will have the number of nodes in the output layer will be always equal to the number of expected output. Example, if I'm working on a classification problem, if it is a 2-class problem, so I can have 2 nodes. If it is a 10-class problem, like a digit recognition, if I want to recognize a digit from 0 to 9, then output layer will be having 9 nodes. Depending upon your problem, the number of classes in your data set, the input and the output nodes will be decided. However, the number of nodes in the hidden layer is challenging and tricky. And it's not like we should have only one hidden layer as shown in the figure. We can have any number of hidden layers. Means we can keep on adding any number of hidden layers. However, we will be having one input layer, one output layer. And the connections also we can decide, like how should be the connections and all those things. Normally, we use a fully connected layer. Means each node is connected to the each node in the its next layer. So that is called as a fully connected neural network. So it's a feed-forward networks. The information or data passes from input layer to the output layer. So now we discussed about this one, the feed-forward networks. So in this, so if I take the example of one node in any in the hidden layer, we can take any node, right? In an hidden layer. So this hidden layer takes input from the previous layers nodes and do some operations, and then it will be passed on to the next layer, right? So if I try to identify which is the basic building block of a neural network is one neuron, or we call it as a perceptron. So it's a building block of our single layer neural network. So the connections, making a interconnections of these perceptrons makes a neural network. Now let us try to see how this perceptron works. So let us take a simple node. So this simple node or a perceptron, it will take a set of inputs x1, x2, x3. Okay, and each input node is connected to this node with the edges, and each edge should have a weight. Let us say we have weights w1, w2, and w3. Now let us try to identify the simplest function. Like I said that this intermediate node will do some operations, mathematical operation, right? So what is that mathematical operation? The simplest one is, it's a sum of product of the input and the weight values. That is x1 into w1 plus x2 into w2 plus x3 into w3, the summation. So in the function we can see. So once we do the summation, we will get some value, and if that value is lesser than or equal to threshold, so we have to identify a threshold, like let us say 0.5 or 0.8 or 0.1. This is a simple case I am giving. So if it is lesser than threshold, the output will be 0 or the output will be 1, otherwise the output will be 1. So what this indicates, 0 or 1, when it comes to 0, it says that the 0 will be passed on to the next layer, right? The node in the next layer, means that edge will not participate in any of the learning process, correct? By edge with 0 means the data will come and stop at that particular node. We will be not able to pass on any data to that one, means the information from that node. If it is 1, whatever the information we have at that particular node, it will be completely passed on to the next node. That node fully active, or we say that it has fired completely. So this is how the implementation. That's why I said the implementation is very simple. It is based on the summation. Entire neural network works based on this principle. The main agenda of this neural network is to identify these weights. So what should be the weights? See, we have the inputs from the user. The weights has to be identified by the neural network, means it has to be learned. So normally these weights are initialized using some random values. So we choose some random values, we give to w1, w2, w3, and we will try to do the operations. The system will try to learn, and there is something as feedback mechanism. So as I said, it's a feed forward mechanism. We have a backward mechanism also. Once we get the final output, so comparing the output, whatever generated by the neural network and the expected output, we will pass on some information stating that, okay, you are doing some mistake here, you try to relearn it. So that time, this neural network, what it will do, it will try to change the weights, w1, w2, w3. So this forward and backward, so entire neural network has two things, forward and backward. In the forward, the information will be passed to generate the output. So once I get the output, we will try to verify whether the output is meeting our expectations or not. If not, we will try to pass on the information in a reverse order, in a backward order, saying that, okay, I am not happy with your the output, try to generate more appropriate output. The system will try to do some operations, a simple mathematical operations, and try to update these weights. So like this way, this process will go continuously for certain amount of time or certain amount of iterations, and then the actual output will be generated. So we will try to see how these things will happen in this session. So this is a simple example. Let us take that we have this input values like minus 0.06, minus 2.5, and 1.4. We have the inputs w1, w2, w3. So if w1 is 2.7 and w2 is 8.6 and w3 is w 2.7, 8.6 and 0.02, we will get an output as 21.34. So this is X. We have not applied still F. So what is this X is? X is sum of the products of the input values and the weight values. So this 21.34 is an input now, and that will be fed to the some function F. That function F will try to do some operation, means try to generate a new output out of this 21.34, and that will be passed on to the next node. Example, if I use the simple thing, if the threshold is, let us say, 10, then what happens? The f of x, f is a simple function, whatever we have here, it outputs 1, and 1 will be passed on to the next node. So this is what. Now let us try to understand what should be this function f. As I said, in the neural network, the main part is the functionality performed by this node. So the output of the node depends on the input as well as the weights that we have given, and it can vary drastically. Because if the data is distributed, we will be having different outputs. Means this x, like for some value it may be 21.34, some value I may be having some thousand, some value I can have like minus 1.5 or something. So there may be a lot of variation in this input to this function. So definitely it will affect the intermediate representation. So probably you may all know that in machine learning, the data should be in a standard format. If the data is not in a standard format, then we may not get the expected output. So normally what we will do, we will try to normalize that data. Means we will try to bring the data into a standard range, like normally 0 to 1, right? Or minus 1 to 1. It depends on my this one, like what should be the input range. Okay, so this function f is more responsible in making data, the output data x, into a some standard range, which is responsible for having a proper intermediate representation, as well as sending appropriate information to next layer. So this entire function f is called as activation function, like because this f of x, the output from this function f, makes the node in the next layer to be active or inactive. So what we can call this one as a activating function. So this f of x can be treated as an activation function, which takes the input x, do some mathematical operations, and it will bring it into a standard range, and that range value makes the node in the next layer to be active or not. If active, to what level it should be activated, that will be decided by the activation functions. Now let us try to understand the activation functions. So there are different kinds of activation functions. We will try to understand. It's very important. So the basic process carried out by a neuron in a neural network is, as I mentioned, takes the inputs and multiplies the neuron weight, add bias. I have missed that one. Along with the weights, there will be one more parameter called as a bias, which is responsible in adjusting the decision boundaries. Okay, and feed the result to the activation function. And this activation function makes the data or node in the next layer to be active. So it's just like a gate function. So we can assume simplest gate function we can assume is a step function, like 0, 1. So depending upon the input, like whatever we saw, the function f of x, like if lesser than some threshold, make it as a 0, greater than threshold, make it as 1. So like that way we can use a step function. But this step function may not work proper in most of the cases. The transformations may not be the maps, whatever we get may not have the proper outputs, and so on. And normally these type of functions are good when we have binary classification. Whenever we have multi-class problem, like if we have multiple outputs to be predicted, like a very good example is a digit classification for multi-class problem 0 to 1. In that case, these step functions may not work. And also, if the data is not linearly separable, then also these things may not be very good. So in that case, we go for advanced functions called as nonlinear activation functions, which will provide accurate predictions compared to the step functions. Let us try to understand the type of different activations functions. The first one is the binary activation function. So in case of a binary step function, as I said, it is a threshold-based activation function. A user has to specify the threshold. So if it is lesser than the threshold, the neuron will not be activated. The neuron will be activated. This type of functions are good for when we have a two-class problem. If it is for multiple class, it can't work properly. So another function, very simple and straightforward, which is better than the step function, is the linear activation function, which is a combination of the different inputs. This solves the problem of the step function. Means it can work for a multi-class problem. But if you clearly understand, as it is a linear function, it's a linear combination of the inputs, right? So even if you have any number of layers, right? So it will be just like a single layer, and the output will be uh, it's just multiplied by the weights of each neuron. So if you use linear activation function, it acts like a simple single layer neural network. Even if you have any number of layers, right? It acts as a single layer neural. So we will try to see this one. Just take a case example. We will generate randomly a two-dimensional data, okay, and we will try to generate an output. So in this code, in this demo, what we will try to understand is, we will try to understand how these weights and bias values are identified, okay, and the internal representation. I told, like, we need to understand the representation. When we give the x1 and x2, it is in the Euclidean space, right? So when we do these operations on h1 and h2, it has been transformed to another space, right? So there, how the data looks, how the transform of the data has happened. So whether when we take a non-linearly separable data, whether it will be able to separable in the intermediate representation or not, that we will try to understand. We will also try to understand how this bias will be generated. So already I have opened my. So you people can do is, you can just copy this link. I have shared that one. So you just it's the URL. So you'll this function will be opened, and you can use this one to run and it. Okay, so however, I have to give permission for you people. I know that you are sending a request this one. So as there are multiple participants, it may be difficult. Or else I will do one thing. I will save these Jupyter notebooks, and I will mail it to Shekar sir. So he will try to share with you people. So it's about illustration of a neural network. So first, this is a Python-based programming I have used. Okay, so I will not to details of the Python programming. So here, the first function, the definition create data. This is used to generate data, a two-dimensional data. So here, what I am trying to do is to generate four sets of data. Okay, means you can assume that there are four clusters of data belonging to two classes. So that I will try to generate. The second function is to plot. So it's based on the random number within a specific range. We are trying to generate it. The next one is the plot data to plot. I have used different plot functions. The first plot is to plot the two-dimensional data. Second plot, the final plot underscore data, and plot line and plot line. There are two plot line functions with different parameters. These are to show the intermediate representation of the neural networks. Like, once we have the input data, and once we perform the operations of the data with the different activation functions, how the data will be, that will be written is written in these functions. Okay, so we create the data like X train and Y train. X train is the feature, and Y train is the class. As I said that I am using a two class data. I have used TensorFlow for learning as of neural net. So what I have done is a program. I have added different different activation functions. So we will be having around some 7 to 8 functions. So in that, I have implemented only 1, 2, 3, 4, 5, 6 other things. I have not added. Another one was step function. I have not added that one. So we can see how this intermediate activation functions transform the data. This one. So we will try to compile the data and we will try to see. I am printing the model weights. So initial model weights, after training, what will be the model weights? Those things we will understand. So I will run all the functions, means all cells of the this one. So you can see that it has been executed. So this is the data generated from my input. As I said, it is a two-class data, and you can see that it is a non-linearly separable data. Non-linearly separable data means just using a straight line, I can't separate this data into two classes. Example, 0 at the mid of this image. If I plot a 90-degree line, a vertical line, right? In that case, also I will be having misclassification, because 50% of the data like blue and dots are on the same region, and another 50% right side it is in the same region. Or from 0, if I try to plot on the feature 2 axis, if I try to plot a horizontal line or a 0-degree, even that will not work. Or if I try to plot from 0 feature 1 to 0.2 feature 2, even in that case I will be not able to separate the data. So this is the input data. Now what is my problem is, I have to design a neural network, okay, so which takes this data and transform the data in such a way that it is a linearly separable. That means my intermediate representation should be strong enough to transform this non-linearly separable data into a linearly separable data in a space, in a hidden space. Okay, let us see. First, I have used the linear function. You can see that here I have used activation function as a linear first one. So remaining activation functions has been commented out. So here you can see the model weights. Here I have not trained the model, right? So here I have just printed the model weights as shown in the graph. Like it had 4 weights: W1, W2, W3, W4, from X1 to H1 and H2 to H2. So totally 4 weights and 2 biases. So in the code, you can see that in the first part, so I have 4 weights which are randomly initialized and 1 bias. Okay, so 1 bias value I have. Same way for the second layer H1 to the output layer, we have 2 outputs, W5 and W6, and also 1 bias. Okay, so we have 2 weights. If you see the last third line, third, fourth, and fifth line, 3 lines, last 3 lines, the last 3 lines, 2 values are weights, and the last line as a bias. This is the next diagram which we have shown. We have plotted with the data along with based on the 2 layers lines. So you can see that it is not linearly separable. So whatever the weights we saw, these are the random weights, and the bias is 0, right? So after that, we are going to train the data. So we have model.fit. I have trained it for around 100. So after 100 epochs, and I have printed the model weights also. So you can see that there is a change in the model weights as well as in the bias. So for both input layer to output layer, hidden layer, and hidden layer to the output layer. Initially, the bias was 0 for our hidden layer, and for the output layer also it was 0. Now after training, the bias has been updated, and also the has been updated. So using these weights and biases, so if you try to plot the data, this is the distribution. You can see that we have an intermediate representation, right? Still, you can see that it's not possible to separate using a linear data. Means we have used linearly linear activation function, which is not capable to understand the understand the data and make it as a linearly separable data. So what I wanted to convey you people with this program is, like in the beginning I mentioned there is an intermediate representation, right? So intermediate representation, if you see the first representation of the data, right? So which was like four clusters now distributed on the axis, and the data distributed like this, and in the final output layer it looks like this, the final image, whatever we have, the final image. So here you can see that the it's been plotted onto a line, okay. So and that's why this one. So if I use this linear activation function on this data, and if I definitely it will be 0.5. So yeah, the accuracy you can see that it is about 0.5, 50% of accuracy. To show like the importance of the activation functions. So we understood that this is what I have done with different epochs. Like when you change with the different epochs. Okay, I have not introduced the word epoch here. So epoch means for a neural network. So let us say I created a neural network, and let us assume that I have 100 input values, okay, of dimension 2, means I have an input matrix of size 100 by 2. So one epoch, if I have a neural network, input layer, hidden layer and output layer, if the data, all the data, 100 data which was used for training, if it is shown to the entire network once, then it is treated as a epoch 1. If I show the same data multiple times, example here 50, means what, the entire data has been shown to the network, or it has been feed to the network 50 times. In the second time 100 times, in the third thing, it is the epoch is 200. So you can see that as you show the data more number of times, try to learn the data more properly. But we have some rules, or we have some limitations also. Show very less, what will be the issue? If we show too much, what will be the issue? It is same like when we are teaching our students, right? If we do, or if a student just read a lesson only once, so he will be not able to perform in internals or in exams properly, right? Same way the neural network may not perform very good. Or if we show the data completely, he will be able to learn properly. So like that way, there are advantages and limitations that we will discuss at the end of this session. Next, we will try to understand what are the limitations with activation function. As we seen, these linear activation functions are just a combinations of the input, right? So even if you have any number of layers, it's just like a single layer, because the last layer will be a linear function of the so linear activity is not good, and they simply like our linear regression model. So means we need to have some more complexity in our activation functions. So for that, we will try to see a different type of function called as non-linear activation functions. So which are very good. Normally, like all the neural networks use non-linear activation functions only, because they have the nature of creating the complex mappings. So when I say creating complex mappings, it is able to understand non-linearly separable data. Even the data is non-linearly separable, or it has a complex nature in the patterns of the data. So these activation functions are very good in understanding this one. And another important advantage of this nonlinear activation functions, as I said in the beginning, like we will be having the feed forward as well as feed backward. Feed forward means we will just give the data to the neural network. It will try to understand and it will produce us the output. Initially, the outputs will not be as expected. So we need to feed back or need to inform the system or neural network stating that this is not what I expected. Try to improve that one. Means I need to send some information backward to the neural network. So that is called as a back propagation. Propagate the information to the neural network so that it can improve in next epoch. So when I say back propagate the information to the neural network, what I will try to do, I will try to estimate the error. The error means I will get the output as well as I will try to, I will be having the actual output. I will try to compare the actual and the generated output and I will find out what is the error. So that error, we will try to give the information to the back to the network. Okay, so it will try to understand and it will try to adjust the weights. That's all. The entire neural network mechanism is it is trying to do the or adjust the weights of the neural network. So this one. So how the weights will be adjusted, at what rate the rate has to be adjusted is very important. So it's not like it should be a random change or it should be very small. At what rate it has to be changed, what direction the function means the error has to be changed. That depends on a mechanism called as back propagation. So there is an algorithm, back propagation algorithms. We will try to see at a higher level how this back propagation algorithm will work. So for this back propagation, the one of the important criteria is whatever the activation functions we use, it should be a function should be like it should have a derivative function, means it should be differentiable. So all these nonlinear activation functions which are going to see now will be a differentiable functions. Now let us try to see differential functions one by one. We will go very quickly. So the simplest one is a sigmoid or a logistic function, and this function is like f of x is equal to 1 over 1 plus e to the power of minus x. Okay, it has a very good advantages. So as I said in the beginning, these activation functions will try to map the data into a standard range. So this sigmoid functions try to map the input value into the range of 0 to 1, means output values are bounded to 0 to 1 and has a very smooth gradient. Why we use this gradient? As I said, this is very much important in our back propagation algorithms, which us to learn very quickly and in a very proper way. So how this activation function will work is, like example, if x is 2, right, or if x is minus 2, means x1 into w1 plus x2 into w2 plus x3 into w3, if it gives a output as 2 or minus 2, because 2 and minus 2 are huge values. Now what it will do, when it is a 2, it maps to 1, and if it is minus 2, it maps to very close to 0, means it will try to give a proper representation. The disadvantage of this approach is it is a vanishing gradient problem. Means if we have a very too large values, right, everything will be mapped to very high, or if it is a too small values, it will be mapped to very small values, which will not participate in further learning. So that is one of the disadvantages, and also the outputs are not zero centered. So normally expect that output to be zero centered. So this sigmoid data or is not zero centered, and it's an computationally explained as we have an exponential term in the this one. So if we try to run our same program, whatever I showed, and if you comment out linear activation function, and if you uncomment the sigmoidal function, the next activation function, we will get the data like this. Now, if see the data distribution, especially in epoch 50, we got the data similar to our linear activation function. But if you see the epoch 200, right, here you can see that all the data belonging to the red class has been merged into one class. So if you see data in the input data, we had two different, right? So this is what the intermediate representation. I think you can appreciate this one, the beauty of the sigmoidal function, right? You can see that we had two red means two clusters of red dots and two clusters of blue dots. So in the intermediate representation, you can see that the red dots have been merged into a single cluster. Or in the output, the last image in the epoch 200, you can see that all the red dots are at the bottom and the blue dots are at the top. And using this, we can have a simple linear line boundary can be generated. So definitely this will generate a very good result. So this is what the use of this one non-linear activation functions. So next to this sigmoidal function, we have another type of activation function called as tan hyperbolic activation function. So this tan hyperbolic activation function output ranges from -1 to +1, and it is zero centered. So which had a disadvantage in the sigmoidal. We have that one. So what this will make, this is a very good thing. Like if you have a strong negative or strong positive values, it will be very easy to map into respective regions. And apart from that, it is same as our sigmoidal functions. Try to see the outputs of this one. So from the tan h function, if you use tan hyperbolic function, you can comment out the second activation function. And if you comment the third activation function for the epoch 200, you will get this representation. Here you can see, like comparing the results of sigmoidal activation function and comparing the tan hyperbolic functions, it is very easy. See, for any machine learning algorithms, if the data is transformed in such a way where we can differentiate in the data in a proper manner, then we can get very good accuracy. Like if you see the input data which is not easily separable using means easily we can't have addition boundary, after transformation, means after using this neural network with appropriate activation functions, the data has been transformed and addition boundary can be generated like this. So these two, sigmoidal and tan hyperbolic functions, were extensively used till this new activation function called as rectified linear unit was designed. See, in case of a sigmoidal function, the output range is 0 to 1, tan h is -1 to 1, and this rectified linear unit, the output range is 0 to infinity. So, what is the advantage of this 0 to infinity? See, one of the major advantages is computationally efficient. Like if you take a hyperbolic or a sigmoidal function, we have exponential terms, and that takes the time to compute, right? So that is the one of the advantages. And moreover, this rectified linear unit is also a non-linear function which can be used, and it's very simple to implement. You can see the function. If f of x is greater than or equal to I think I made a mistake. If it is greater than 0, x, otherwise it should be 0. So this rectified linear units is very good. Normally in most neural networks, and especially in deep learning, deep neural networks, in tomorrow's session you will try to understand, like we are going to use these rectified linear units. The major disadvantage of this rectified linear unit is dying ReLU problem. Dying ReLU problem means if the x, the input value, is lesser than 0, what happens? It will be mapping to 0. Means it is not able to use the data which are having the values lesser than 0. So the nodes which are having this one 0 will be, many nodes will be generated. Means those nodes will try to make many of the nodes in the next layer to be more active. So because of that, If we have a multiple hidden layers, we will have a die, means it will not activate the nodes in the previous layer. This is one of the major problems in the this creates a problem even in back propagation. When we are back propagating, so it will not be very good. Data, the intermediate representation, we will directly go to the epoch 2, the hidden layer representation. You can see like how it has brought all the data into one particular region. However, we have an outlier on a red on the top X, right? So, but it is better. Like we can get good results. For this data, it works like this. So next one is leaky ReLU, which is a modified version of leaky ReLU, which gives a certain flexibility for the negative values. Like it is same, like max of 0.1 into x comma x. So it will try to generate this one. So from the diagram itself, you can see that even it works for negative values, but it will be having some issues, means negative input values. It says that ReLU, it has been used. So this is the analysis of leaky ReLU. The next one is a parametric ReLU, which parameter is added. In the previous leaky ReLU, it was 0.1. Here the alpha is there. The user can specify the alpha, and based on that, you can specify. The last one, the recent one proposed by Google, is the Swiss activation function, which says that which is better than our all other this. So this is the representation of the Swiss activation functions. So what we try to understand from these activation functions are like these activation functions transforms the data to another version, which is very good for the next layer, means for the next hidden layer or for the next output layer. So normally all these activations functions are used in the hidden layer. However, we can use it for the output layer, but recommended is the softmax function. Like a softmax function is a activation function, which is a generalized version of the sigmoid or logistic activation function. Sigmoid or logistic functions are very good for binary classes. For multi-class problem, if I want to get the predicted values in a probability range, like 0 to 1, and distribute, if it need to be normalized, then we use the softmax function. Normally the softmax function is used in the output layer. Even in the output layer, we'll be having a f of x. That f should be softmax. Almost we use softmax. However, it is not mandatory. We can use others also. So said that in the beginning, like whenever we generate activation functions, it should be a differentiable function. So this table will just give equations with respect to the differentiation functions. So now you can see for identity, means linear, and for step functions, the derivative, they are not good. So they will not work proper in case of backward propagation, because it will be either constant or be 0 or something. It will be not good. Whereas in all other cases, this have derivative functions, means they are differentiable and backward. We can use these functions, and these supports for backward propagations. Now let us try to understand how this neural network works. Now we understood, like there will be an input layer. Mainly we are working on weights, identifying the suitable weights, and also we need activation functions to make the nodes in the next layer to be activated. So except in the input layer, the hidden layer and the output layer will have the activation functions. So that should be made clear. The input layer does not have activation functions. Hidden layer and output layer will have the activation functions. And the number of nodes in the input layer will be equal to number of features in the data set, and number of nodes in the output layer will be equal to the number of classes in the data sets. The hidden layers, the number of hidden layers, it is an artistic, we have to design, and the number of nodes in the hidden layer is also artistic, or it's normally it's set by experimentally. So we will try to see how those things can be identified. Let us take this data set, a simple data set which is having a two class. So in case of a two class problem, as I said, like we can have two nodes, or else we can also implement with a single node itself, means just output as a 0 or 1. If 0 class can be identified as a class 1, 1 can be identified as a class 2. Only for case of two class, we can have one node or two nodes in the output layer. Whereas for all other data sets which are having more than two class, we need to have the number of nodes equal to number of classes in the data set. Let us take a simple example. Let us initialize with a random values. Let us assume that all the weights initialized. Now let us try to present a training pattern. The first sample 1.4, 2.7 and 1.9, and expected is 0. With the random weights, let us say the output generated is 0.8, but the expected is 0, right? So what is the error? The error is 0.8. We expected 0, but we got 0.8 as an output, so the error is 0.8. Now what we need to do, we need to adjust. Like if I want to improve this one, what I need to do, I need to adjust the weights. So if I change, definitely there will be change in the output value, because see, we can't change the input values. Input values are always fixed because it's a data set. Only what we have in our hand to change is the weights of the neural network, or the weights of the edges, right? You try to adjust the weight so that the error will be decreased. So we will try to keep on doing this one. We will try to show another data. We will try to see what is the error, try to adjust the weights and so on. So if there are, let us say that there are four data points here, right? Four samples are there. Four samples will be passed on to the network one by one, and we will try to adjust the weights. So if I say one epoch, the neural network, whatever shown on the screen, that will be the all the 4 points, 4 sample patterns will be fed to the neural network. So that compromise of one epoch, and the weights will be updated. In the next epoch, once again, these 4 samples, all the 4 samples will be fed to the network. Like that way, we can feed it multiple times, and we will try to adjust the weights until we get the expected values like 0, 0, 1, 0. So this has to be continued thousands of times, hundreds and thousands of times, until we get the expected output. So during this epochs, what it will do, it will try to update the weights. But we have not understood how the weights are updated. We will try to understand. But let us come to a conclusion that we have updated the weights using some. So when we are showing the weights epoch by epoch, what is going on? It is trying to identify the boundaries. So means the boundaries will be getting adjusted. So this is what it will try to adjust the boundaries in a proper way. So this is what the training does. Means when we say the neural network is getting trained, or in general in any machine learning algorithm, when we say training is happening, it is trying to find out the boundaries, a proper boundaries for the given training data. So this is what the neural network. So important note, what we have to understand is this neural networks are dumb in nature. Dumb in nature means, see, we are not doing anything. Means just weight updation rule. We have to understand how this weight has to be updated. So if the weights are updated in a proper manner, right, we will get a output value. And these adjustments are not like one time or two times. As I said, like it has to be executed hundreds or thousands of times, right? So it's a tiny improvement, it's a very small improvement. Sometimes it may be very worse if you have a data which is not proper, you may not be able to identify the proper weights and you may not get the actual output at all. So it's just a trial and error approach, this one. Uh, in a generic sense, it is a trial and error approach. However, we have some mechanism that makes the task of updating uh, weights in a proper manner. So that approach is called as a back propagation algorithms. So how this back propagation algorithm works? See, as I said in the beginning, like we have data means this neural network has a two pass algorithm, like forward pass and backward pass. In the forward pass, the input data will be fed, okay, and it will try to generate the output values for all the data whatever we have in the training set, right? And we will calculate the what is the error. Once we get the error, that error has to be passed to the previous layer, means it will be in a reverse order from the output layer. So if I have an output layer, so that output layer will be connected with the hidden layer, the last hidden layer, using some edges, right? So those edges will be having the weights. Now I need to say, okay, I got this much the output, but the expected was this one. So there is some error. Just find out the difference. So I will get the error. I will try to show this was the error I got based on these inputs. And this back propagation algorithm, what it will do, it will try to see what was the problem. So it will be a problem in two things. One is like the weights what we have used, the f of x and means the x. So now I need to update this x, right? When I say x, it will be having two things. So that x obtained based on x1 into w1 plus x2 into w2 plus x3 into w3. So I need to update weights w1, w2, w3, as well as we will be having another parameter called as a bias. So b naught, right? So these two parameters has to be updated. So how can I update? So it's a simple mechanism. So see, this back propagation, it can be implemented in several ways, and also we have different techniques. I have taken a very simple approach, a straightforward approach. So let us study about delta rule. This delta rule is a specialized version of the back propagation learning. Okay, so what it will do, it will calculate difference between the generated output and the actual output. So we will be having two output, let us say t minus o. T means generated and o means the actual output. So this beta is the error term. So this gives what is the difference between these two. Okay, so based on this, we will try to see how much of change we need to do in the weight. So delta W. So that delta W is a parameter which says like how much amount of weight which is coming to that particular node has to be changed. So if I have a W as a weight, input weight for a particular node, so based on the beta, so beta is the error, right? And x is the input. So we will be having a x parameter which is multiplied by w, right? X1 into w1 plus x2 into w2 plus x3 into w3. So if I take w1, the input is x1. So that x, the error term, and a learning rate. There is another parameter called as a mu, which is called as a learning rate. This is also very important parameter in a neural network. So this learning rate tells how fast I should learn. So the learning rate can be very small or it can be very large. If it is very small, so definitely delta W will be very small. Then the weights updated becomes very small. So the learning will be very slow. If mu is very large, so the delta W will be very large, and W plus W, delta W yields to a new W, which will be different from actual W. Then the learning will be very fast. So when I say learning is very fast means it is a process of moving towards the actual goal. See, my goal is t minus 0. The error should be 0, right? Sorry, t minus o. the target and the actual output, if I take the difference, it should be very small. My goal is I need to make this error. My optimization function is my goal of the optimization function is I want to make this error as small as possible or make it as a zero, right? So if I use a small learning rate, the number of steps I may require to move to that one may be very large. Means too much of steps may be required. Means too much of training of the neural network may be required. Okay. On the other hand, if I use large, okay, I will take a large step. I will use a large learning rate. Then what happens? I may jump from the actual goal itself. That is the main problem. So in order to regulate that, we need to identify the this one. So this entire process, W is equal to W plus delta W, is a process of updating the weight. It's a very straightforward approach, and for using the delta rule. Okay, so and it's a chain rule. Chain rule means, like, let us say if I have a single hidden layer, what happens? I need to update the weights. First, I have to update the weights from hidden layer to the output layer. Okay, and then I have to update the weights from input layer to the hidden layer. Same way, if I have two hidden layers, means input, hidden layer 1, hidden layer 2, and output layer. Now it will be output layer to the hidden layer 2, hidden layer to the hidden layer 1, hidden layer 1 to the output. Means it's just like a chain. We can do that one, and like that way we can do this one. So that's why the entire learning rule, the delta rule, work like this. Generate the output. So compare with the desired output. So it's identify what is the difference in that one, and try to update the weights, right? That W and all those things, and give once again. Once the weights are updated, feed the data once again. Try to see the output, and compare the output. If the desired output and output difference is very small within our expected range, then we can stop the training, or we have to do this process. So there are different ways of back propagations, means implementations. I think you people can go through that. But this is the simplest one, and implementing in Python also is very straightforward. This is an example of convergence. So here the goal is at the bottom, the final value. In the graph, if you see the final value, so if it is a starting point, if I start here, so there are three different cases. So what I will do, I will put a learning rate as a constant, let us say 0.1 throughout the training. Then we have a blue line, like to the left side, you can see that it will move step by step towards the goal. On the other hand, if I use a large learning rate, what happens? So initially it may move nearer to the goal, but it may jump in the second iteration or some other iteration. It may jump and it may not come to the final goal. Normally we call it as the optimal, this one, or mean value. Whereas the last approach is we can have an adaptive learning rate. Adaptive learning rate, or something, or a strategy, simple strategy is, if I have some 100 iterations, what I can do is, like, initially I will try to take a large steps for some 30 or 40 epochs. After that, I will reduce the learning rate by 50%. After that, after some 50 epochs, I will try to reduce the learning rate 0.25%. Like that way, we can reduce the learning rate. Initially, we can have a large rate, reduce the learning rate. So comparing to these things, the third approach is better. So these things are available while programming, like either if you use any Python tool, means platforms are TensorFlow or Cafe, you can specify these options, and we will see how these things will work. So this is a general neural network thing. So just to summarize about the neural network, how this neural network works. So we have to design a neural network. In that case, the number of nodes in the input layer will be equal to the number of features in your data sets. So we can have the hidden layer, and we can have the output layer. So output layer, we can have the number of nodes equal to this one. So overall, so input, there will be an hidden layer. So the hidden layer, it do some operation f of x. So f can be any activation function, but x is the summation, sum of product of the input values and the weights. So that is what a of j. And hidden sigmoid, like you can use any activation functions. The output will be forward to the output layer, and also at the output layer we should have a activation functions. Normally we use a softmax. However, we can use a sigmoid or anything, like if it is a binary 0 to 1 if you want, or minus 1 to 1 if you want output like minus 1 to 1 like SVM, we can use tan hyperbolic functions. Okay, so this is what how we design the activation means a neural network is. Normally we take a input layer. Okay, let us assume there are m features. We will try to have m nodes in the hidden layer. Initially we will try to have the m hidden layers and one output layer, assuming that it's a binary class problem. So we will try to connect it fully connected way, and we will try to generate the outputs. If you are not getting the appropriate approaches, what you can do is you can remove some connections. We call it as dropouts. So there is a mechanism. I will explain what is a dropout, where we can remove the nodes during the, not nodes, the edges during the training. So this will have a good generalization problem. So as I said in the beginning of what neural networks are why, right? So the neural networks are very good in generalization. If my neural network wants to be a good generalization, normally we use a dropout, so that some connections will be missed in one epoch, and in another epoch we will try to remove some other connections. Like that way, if you try to do it, it will be having a very good accuracies. Or else we can have the number of nodes in the hidden layer lesser than m. Normally we choose this strategy. So the number of nodes in the hidden layer will be always lesser than the input layer. Or normally the hidden layers, any layer, if I take any layer, previous layer, the number of nodes in the previous layer will be larger than the current layer. So just to summarize, as we saw in our demo and the programming, so if we have a zero hidden layers, it is very good for linearly separable data. For non-linearly separable data, it is better to have at least one hidden layer, which can have this type of representations. So like this way, we can try to increase the decision boundaries. So till now, we only about a single class, right? Same way, we can have multi-class. We can have any number of classes, like example of digit classification or something. That's all. And also deeper neural networks means what? So if this is the one single hidden layer architecture, just try to add one more hidden layer, and those things will be connected like A1, B1. You can keep on adding this one. So this makes the neural network deeper and deeper. So uh, what we will do, I will just open these two demo, and I will try to show you how this for iris dataset, it's not for image, and how this multi-class MNIST can. I have loaded a iris dataset. So iris is a flower dataset. Most of you may be knowing that one. So it has a three class, and it has four features. So in order to implement a neural network, so normally we need to import some functionalities or packages like NumPy, Pandas, and all those things.